Hi everybody, this is Mr. Polly. Oops, I don't have my drawing part on yet. And I am sorry I'm ditching you on class today, so I thought I would just go over some of these problems and we would roll from there. So these are the ones that were assigned. I know the answer keys are there, but I want to tell you how I would address them and how I think what the tricks of them are and other little changes that might happen. The student performs an experiment to determine the molar mass of an unknown gas. Okay, so as soon as I see this, I think of my equation that has molar mass in it, which is PV equals mass RT over molar mass. The other thing I sometimes think of is moles equals mass over molar mass, which if you notice is, whoops, I did that a little more than I had that a little over highlighted. Well, mass RT over molar mass. I'll try my highlighter again. What? Should I have tried with the dot outlines? Sure. So on this one, you can see that mass over molar mass is in both of them, although this is mass. Okay. So I think equations right away when I can tell something's a lab situation like this. A small amount of the pure gas is released from the pressurized container and collected into a graduated tube above water at room temperature, as shown in the diagram above. The collection tube containing the gas is allowed to stand for several minutes. What that means is the temperature is going to be equal, okay? And the depth is adjusted until the levels inside and outside are the same. What that means is that the pressure is going to be equal, okay? Assume that the gas is not appreciably soluble in water. What that means is the volume of the gas is the same as the volume of the cylinder. The gas collected in the graduated tube and the water at thermal equilibrium, and that would have, could have, should have been a question. A barometer, a thermometer, an analytical balance, and a table of the equilibrium vapor pressure of water. This is where it says, hey, silly, don't you forget to subtract water. At various temperatures are also available. Write the equations needed to calculate the molar mass of the gas. So this is equation, that's an equation we need. The other one is the pressure total equals the pressure of the gas plus the pressure of H2O, because those are the two things that are in there. The other thing that I need, so what I do to make sure I have this, I know this is like I call it my mama equation. Do I need to do anything to get pressure? Nope, that comes right from a barometer. Do I need anything to get volume? No, volume comes right from my graduated tube is what they called it. Do I need anything for R? That's a constant. Temperature is the same. Molar mass is what I'm calculating. I do need to figure out how did I get the mass again. So the way I got the mass is the mass of the full tank minus the mass after release. And that's going to equal the mass of the gas. I'm sure you're not surprised that this is the most forgotten one. So the way you make sure that you don't forget any of these, if it asks you to list the equations, the way you do that is you make sure that you think of the mama equation, the last one, and backtrack each one to either measuring it with a balance, say mass is a balance, or a graduated cylinder, or a barometer, or a thermometer. Okay. Explain the purpose of equalizing the water levels inside and outside the gas collection tube. Okay. See if I can write this small enough. Okay. If the, whoops, I want to put it over here. If the water levels are equal, the pressure in the tube equals the pressure outside of the tube. So our barometer can tell us the pressure of both. People forget this last part. The barometer can tell us the pressure of both. Having the pressure be equal doesn't mean you can get the answer, but indicating that the barometer can do that works. Student determines the molar mass of the gas to be 64 grams per mole. I circle the numbers they give me all the time, except for I missed on that one. Write the expression set up for calculating the percent error in the experimental value, assuming that the unknown gas of butane, the molar mass is 58. The molar mass of the gas to be 64%. Okay, so to find the percent error, that's the percent wrong. This is the way I do it, and you get credit for this. Equals part wrong over total times 100%, which would be the part that's wrong would be 64 minus 58 over the unknown gas is butane over 58 times 100%. Okay. Now, sometimes what people say is expected and all this other stuff. Now, notice this gives you a positive value. What you'll see a lot of times is expected, and if you were taught this way, this works. Wait, no, it's actual minus expected. Yeah, expected minus actual over expected times 100%, which if you notice is almost the same thing because it would be 58 minus 64 and then over 58. Whoops. Come on, eraser. Boy, my eraser doesn't like to be erased today. Over 58. Now notice this will give you a negative value, but remember the percent error just tells you how wrong you are. The negative gives you the direction. So either one of those should be fine. E. If the student fails to use the information from the table of the equilibrium vapor pressure of water in the calculation, the calculated value for the molar mass of the unknown gas will be smaller than the actual value. Explain. E. So remember the equations that we had up here, P total equals P gas plus pressure of the water. So the pressure of the gas is the pressure total minus the pressure of H2O. If you omit pressure of H2O, then P gas is too high. I'll let that settle. Oh well. In PV equals mass RT over molar mass equals RT over PV. And if P gas is too high, algebraically, meaning this number is too high, and I like algebraically because you don't have to explain any more than that. Algebraically, molar mass is too high. All right, so I hope that works. I get to go on to my next problem in a different color, I hope. All right. I'm using the ones from the 90s because I think they're a little bit harder. There are other gas problems that are a little more recent, but and you'll probably see one of those on your quiz. Student collected a sample of hydrogen gas by displacement of water as shown on the diagram above. So this is the other way you generate a gas and collect it over water. So you would typically have a tube with a reaction going on. So say I put magnesium and this is extremely common. It might even be what's on your test. MgCl2 plus H2, and H2 is the gas. Okay, and when that makes bubbles, and you got a little cork in here with a tube, that tube then goes right into here. Okay, it doesn't have to be hydrogen, but you get the idea. Okay, student collects a sample of hydrogen gas by the displacement of water as shown in the diagram above. The relevant data are given in the following table. Boom, 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 boom. Calculate the number of moles of hydrogen gas collected. So when I hear moles and I hear gas, I'm thinking, sweet, PV equals nRT. The atmospheric pressure, now let's make sure they equalize the water level. They did. So my pressure is 745 millimeters of mercury. Now I'm going to tell you they don't do this to you anymore, but I did give to you in the podcast that if you divide by 760, that will get you into atmospheres. So I'm going to do that right now. 745 divided 760 is 0.980. And whenever I know there's an automatic conversion, I never like to write it down in my math because I'm much more likely to get excited and miss it. I don't know why I sound so calm and cool and collected today. But the volume of the sample is 90 milliliters. No, not 90 milliliters, 0.090. I'm going to put liters on there. So if you recall, this is the one that's pretty darn picky about it. We're solving for N. R is 0.0821, as long as I'm using liters and atmospheres and moles Kelvin. And then there's R and then T. No! Remember, I have to add 273 to get that there. So that's 298. And then I do the math. Whoops, I just misspelled N. That's pretty funny. 0.98 times 0.09 divided by 0.0821 divided by 298 is 0.00361 moles. That number seems really small, so I'm going to run it again. 0.98 times 0.09 divided by 0.0821 divided by 298. I got the same thing twice, so I believe it. Okay, so there's A. Calculate the number of molecules of water vapor in the sample of gas. I know what I did. You know what I did? What I tell you not to do. I used the wrong vapor pressure. So this is where I say frickin' dickens. I get mad at myself. I yell, I scream, I get mad. And I have to do 745 minus 23.8 equals 745 minus 23.8 equals 721 over 760. And that is 0.948. Okay, so that means I have to change, whoops, why'd you do that? That means I have to change 0.948 and 0.980. And that's just what I'm gonna do. I'm gonna change this to a color of shame. Okay, so again, do you see how easy it is to forget about that? I did it, and my goodness, I'm a professional. So that means this number is also going to change. So 0.948 times 0.09 divided by 0.0821 divided by 298 is 0.0039. Oh, get my pen back. 0.00349. Not the biggest change, but it matters in your score, that's for sure. Okay, so okay, number of water molecules. So that means I have this many moles of water. So now to do molecules, 0.00349 moles times 1 mole on the bottom, 6.02 E23 molecules on top, times 6.02 E23, 2.10 E21 molecules of H2O. And that is B. All right. So for C, calculate the ratio of the average speed of hydrogen molecules to the average speed of water vapor molecules. This one you don't have to do anymore. What they would ask you is which one's faster. So if there was a small hole in it, which one would escape faster? And remember, smaller equals faster. And I'm going to change the word smaller to lighter, because that's true. So lighter equals faster. So that means that H2 is faster than H2O because this weighs 2, this weighs 18. That's C. D. Which the two gases deviates most from ideal behavior? Explain your answer. For D, we're going to talk about size. H2O is larger and deviates more. We're going to talk about attraction. H2O, for two reasons, has more attractive forces. H bonds and more dispersion forces. Okay. And there you go. All right, number 5. Let me change to yet another color. I wonder if some, oh, this says it's dark gray. That was black. In an experiment, a student synthesizes that big ugly thing by reacting aluminum metal with potassium hydroxide and sulfuric acid as represented in the equation above. Wow, that's a big honking equation. In order to synthesize alum, the student must prepare a 5 molar solution of sulfuric acid. Describe the procedure for preparing 50 milliliters of 5 molar H2SO4 using any of the chemicals equipment used before. We haven't done that yet, so you're okay. Oh, we haven't done that yet. That's okay. Okay. Okay, so all right, we did do C before from a previous one, so that's one we can talk about very briefly. As the reaction cools, the alum crystals precipitate. The student filters the mixture and dries the crystals, then measures the mass. The student weighs the crystals before they are completely dry. What would the calculated percent weight be? So remember, the crystals they're trying to get are these crystals right here. So we're looking for a percent yield. So that's going to be product over expected. Right? So if our product is still wet, then it becomes product plus water. So it's product plus water, algebraically. Product plus water gives a higher percent yield. Number 2, cooling the reaction solution in an ice bath improves the percent yield obtained. Explained. This is new, but it's so short I can add it for you. Cold water is less soluble for solid precipitates. So yield improves. D, the student heats crystals of pure element in an open crucible to obtain a constant mass. The mass of the sample after heating is less than the sample before heating. Explain. Heating removes H2O and keeps ionically bonded. And it's ionically bonded because it's metals and nonmetals. Ionically bonded alum. Okay, so now I gotta find my other one. Okay, so these are here are the gas law problems that I want to do. So let's get into drawing on these. Have I mentioned I love my new computer? Because I do. Answer the following questions related to hydrocarbons. Determine the empirical formula of the hydrocarbon that contains 85.7% carbon by mass. Okay, hydrocarbon means it's hydrogen and carbon. So that means it's 0.857 grams carbon and a 0.143 grams of hydrogen. All I did was 1 minus 0.857. Okay, and now I'm doubting myself because I'm live. 1 minus 0.857 is 0.143. And then it's going to be 1 mole. It's going to be 1 mole. I do want to point out that this is for H1, not H2, right? Sometimes we diamaticize, well, let's go with that, hydrogen when we shouldn't, and it rarely do you have a chance to, but this is the one time it doesn't happen. 0.0714 moles, and then 0.143 divided by 1.01 is 0.141 moles. I should have known that. 0.1415 moles. And then, if you recall, what we do is we divide by the smallest. Okay, so to get the empirical formula, we're going to divide by the smallest. 0.0714 this is going to be 1. This is going to be 2. Okay, so that means this is going to be C1H2, and I really wish you wouldn't put the 1 there. And I really wish I could get rid of my 1 there. There we go. The density of the hydrocarbon in part A is 2 grams per liter at, okay, now here, because they gave us a pressure, that tells us it's a gas. Okay, otherwise you're not 100% sure what it's going to be. So let me show you how we get that equation. PV equals nRT. Big surprise here. PV equals mass RT over molar mass. Hey, I've seen that one before. Now remember, density is mass over volume, so I'm going to cross multiply here. PMM equals mass over volume. That's density, RT. So then what that means is, and you can just write this down and remember it or have it somewhere that's helpful, but know you can derive it. Density equals, I'm going to move this to the bottom, PMM over RT. Okay, so the density of a hydrocarbon in part A is 2 grams per liter at 50 degrees Celsius. I hate you, 50 degrees Celsius. So 50 plus 273 is 323. 0.0821. And then it tells us the pressure is 0.948. That pressure comes from right here. And then molar mass. Calculate the molar mass. Hey, I can do that. 2 times 0.0821 times 323 divided by 0.948. And I get 55.95. So I suppose I should call it 56.0, but that's okay. Determine the molecular formula of the hydrocarbon. So what this means is I'm going to call this, because I'm a 3 sig fig kind of guy, because that always gives you the right answer. 55, I did it wrong, 56.0 grams per mole. I just rounded it to 3 sig figs. So 56 grams per mole is the formula of all of it. So 56 divided by, remember, carbon is 1, hydrogen is 2. 12 plus 2. 56 divided by 14 gives me 4. So I'm going to multiply C1H2 times 4. I'm going to get C4H8. There's my molecular formula. All right. 2 flasks are connected by a stopcock as shown below. The 5-liter flask contains CH4 at a pressure of 3. And the 1-liter flask contains C2H6 at a pressure of 0.55. Calculate the total pressure on the system after the stopcock is opened. Assume the temperature remains constant. Okay, I'm going to use the big empty space down here. Okay, so So remember, this is where we have to do this twice. CH4, I'm going to do P1V1 equals P2V2. P1 is 3, V1 is 5, P2 we're solving for, V2 is 5 plus 1. 5 plus 1, that's just 6. P2 equals 15 divided by 6. Notice how the pressure goes down a little bit? That makes sense, right? It's a bigger container. The other gas was C2H6. Same thing. You don't have to write PB twice. You have to write it once. The original pressure is 0.55. Original volume is 1. New pressure is what we're solving for. Volume is 6. So 0.55 times 1 is 0.55. Divided by 6 is P2 equals 0.0917. So P total equals pressure of CH4 plus the pressure of C2H6. Hey, we don't have to add the vapor pressure of water because it's not collected over water. So this is going to be 2.5 plus 0.0917 and 2.5 plus 0.0917 is 2.59 atmospheres. Okay, good. All right, last one, I believe. Oh no, I got another one. All right, last one. Octane, C8H18, has a density of 0.703 at that kind, blah, 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 blah. So that means I've got to get moles from that, okay? So we did density a minute ago, where density equals PMM over RT. Was that what it was? Yeah. Oops. Let me erase that. Actually, you know what? I want all this space. It might be the same gas. So that means we might know its density already. AP chemistry likes to do that, but doesn't always do that. So let's take a look. Okay, so octane has a density of that. A 255 milliliter sample of C8H18 measured at 20 reacts complete with oxygen, excess oxygen gas represented by the equation below. Okay, so what we have to do is this is the density in grams per milliliter, and I have this many milliliters. So density equals mass over volume. The density is 0.703 equals mass over milliliters. Now I got to check to make sure my units jive, and they do. So a little math here, 0.703 times 255 is 179.3 grams of C8H18. It reacts with excess oxygen, so that means I don't have to do that limiting reactant stuff we were talking about before. So 179.3 grams of C8H18. And it wants to know how many moles of gas are produced. So what I'm going to do is going to convert this into this and convert this into this. Now, if I was a mathematical genius, do you see how 2 moles of this will give me 16 moles of this and 18 moles of this? If I was a mathematical genius, and I wasn't in high school, but I see it now, do you see how 2 moles will turn into 16 plus 18, which is 34 moles? So I could do this a whole lot shorter if I would have recognized that. So what I'm going to do now is do it the long way, because that's what I would have done in high school. I'm going to the periodic table to get the molar mass of octane. So 8 times 12.01 is 96.08, and then plus 18.18, because there's 18 hydrogens. That's 114.26. Okay. So, and then I'm going to do this, and I'm going to have 2 moles of C8H18 and 16 moles of CO2. Now notice it just says how many moles form. Okay, so if you do this, you'll get it, and then you can do the same thing again. 179.3 grams of C8H18 times 1 mole C8H18, 114.26 grams C8H18 times, in this case, I have 18 waters and 2 moles of octane. And I get a number. So 179.3 divided by 114.26. I'm actually going to do the times 34 when I'm doing this now. I would get 2 numbers here and add them up. No, I'll do it the way I said I would. 179 clear. 79.3 divided by 114.26 times 16 divided by 2. Well, by the way, yeah, that's fine. That gives me 12.6. 179.3 divided by 114.26 times 18 divided by 2 gives me 14.1. I'm going to add those two together. Whoops, I hate when it does that. 14.1. I'm going to add those two together and get 26.7 moles. Okay. All right. A last one. Consider 2 containers of volume 1 liter at 298 K as shown above. One container holds 0.1 moles of N2. The other contains 0.1 moles of H2, labeled properly. The average kinetic energy of the molecules is this. So average kinetic energy I relate to being like temperature. Notice their temperatures are the same. Assume that N2 and H2 exhibit ideal behavior. Okay. Is the pressure in the container holding H2 less than, greater than, or equal to the pressure of the container and N2? Justify your answer. Okay. So there's 2 ways you can do this. One is everything's the same. Okay. If I was in high school, I loved the math. I would have done PV equals nRT twice, and P is equal, right? So what happens is P equals nRT over V. Do you see how all of these are equal? So they're all the same, right? You don't know how many moles there are, so the moles would be the same. So I would do it with math. You could also do it with words and saying if, and the words basically are the same thing. If the volume is the same and the moles are the same and the pressure is the same, it doesn't matter what gas is in there. And said ideal gases all act identically. Okay. What is the average kinetic energy of the H2 molecules? Okay. So realize the average kinetic energy is going to be the same, but I'm going to put a star on there because I know the speed is not. Okay. But they're the same because the same temperature. Okay. The molecules of which gas, N2 or H2, has a greater average speed? Justify your answer. And remember I said the big kid is the slow kid, right? So hydrogen is 2.02. Nitrogen is 28.02. H2 is faster because H2 is lighter with the same kinetic energy. Or you could start off with, you know, I love my equations, Ke equals 1/2 mv squared. H2 is lighter, therefore algebraically faster. Algebraically faster. Yeah. Okay. What change could be made that would decrease the average kinetic energy of N2 molecules in the container? Remember how average kinetic energy is basically temperature? You could cool it, mister. And it doesn't ask us to explain it, so we're lucky. If the volume of the container holding H2 was decreased to 0.5 at 298 K. So notice that temperature is going to be the same, but we change the volume. What would be the change in each of the following variables? In each case, justify your answer. Okay, so what we can do is write the equations for it. Okay, so P1 over T1 equals P2 over T2, and then say algebraically. Okay, average speed of the H2 molecules would be the same, and then you do kinetic energy equals 1/2 mv squared. Nothing changed. Algebraically. Okay, so for this one, that's an okay answer, right? What people like to see is they like to say, oh, you don't understand the concepts, which I think is poo-pooey. So the volume of the container holding this was decreased. So if volume goes down, if I were to give it to you in words, if volume goes down and particles are moving the same, there will be more collisions with the container, increasing pressure. And if I did this, I can't just say P1 over T1 equals P2 over T2. I would have to then substitute, right, and solve it. Okay. A different compound, which is the empirical formula sugar, has a vapor density. Vapor density is the same thing as density. That just tells you it's a gas. Using the data to determine the molar mass of the compound and the molecular formula of the compound. Okay, so what we're going to do is the same thing for density. So density equals PMM over RT. So what will that tell us? What I want to do is I want to use PV equals nRT. So what I think I'll do is I will use PV equals nRT. PV equals nRT. Yeah, well, let's do that. Yeah, let's do that. So if I do PV equals nRT, does it give us a pressure? Yes, the pressure is 0.983. The volume, it doesn't quite tell us, but see how this is the number of grams in 1 liter, right? So it's like, oh, so that means my volume is 1. And instead of moles, I'm going to change that out right now to be mass RT over molar mass. Okay, so 0.983 times 1 equals 6 grams, 0.0821. My temperature was 375. Yay, it's Kelvin over molar mass. And I'll solve for that. So when I tell you, when in doubt, do PV equals nRT, and then you start to fill in some stuff, right? And it helps. So remember, density gives you grams per 1 liter, so that helps us get there. So 6 times 0.0821 divided by 375 divided by 0.983. Ooh, that can't be right. 6 times 0.0821 times 375 divided by 0.983. The one I got before was less than 1. So my molar mass is 187.92 grams per mole. If I were to sig fig that baby up, I'd call it 188. I put 118. 188 grams per mole. So that's the molar mass. To check. Molecular formula is going to be find this guy, CH2Br. I'm going to go to the periodic table. I'm going to have 12.01 for carbon plus 2.02 for hydrogen plus 79.90 for bromine. And that's not right. 12.01 plus 2.02 plus 79.90 is 93.93. So I'm going to do 188 over 93.93 and 188 divided by 93.93, and I get 2.00. So this times 2 is going to be C2, double that, H4, double that, BR2, double that. Cha-cha-ching. Oh, man. I'm skipping that one. All right. Thank you guys so much for your patience. I apologize I'm not there. On Wednesday, it'll be due Wednesday after we have class in case you have anything else, which I know is kind of evil and shady, but I hate missing 2 days. So I'm going to tell you that you get a little extra cheating on that one. Toodles.